Hello again. We are talking about the inversion of the CDFT. And last time we carried out an important part of that by showing that the CDFT is injective. Now, when I teach this course, I always emphasize that, so we gave a proof of this statement, but that you shouldn't expect a statement like this to be easy to prove. And so, it's not, there are certain kinds of things that we do in this course, which, sort of, I may not give a proof for it, but it falls into the category that if you think hard about it for a day, then or at most a day, then you can figure out at least an outline of a proof yourself. And there's other things that that I state without proof that you absolutely should not expect to be able to recover in a day. And this this fact is one of those. And there's been a number of them, especially concerning things about measure theory and integration, right? But this is one in the category of Fourier transforms. Okay, so we will continue today talking about the inversion properties of the CDFT, and so the CDFT is injective, okay. And one can show that it's not surjective. And this isn't a gigantic shock. Why did we come up with this space? So this space was just comes from the Riemann-Lebesgue lemma, and there's just nothing about the Riemann-Lebesgue lemma that says for every discrete frequency signal decaying to zero at infinity, that there should be something in L1. So that's the CDFT of it. There's just no reason to expect that to be true. And it's not true, okay? So you can do this in one of two ways. One way is to actually put together an actual discrete frequency signal, which you somehow show is not in the image of the CDFT. And then there's a more abstract way to do it, using a little bit of functional analysis. Okay, but neither way I'm going to talk about. Okay. And one of the reasons that I don't want to dwell on it, there's lots of other reasons why I don't want to dwell on this, but one reason is that the surjectivity of this mapping is not so important. It's the injectivity that we really care about. And so injectivity, as I mentioned last time, ensures that there is a left inverse okay. And I'm going to call this left inverse because we're actually not going to really use it or calculate it, so it doesn't matter if I use notation. I'm going to write it like it's an inverse. It's not, but because this thing, of course, isn't invertible because it's not surjective. So by an abuse of notation, the left inverse I'm going to write as FCD inverse. And it should take a sequence or a discrete frequency signal here and give me something in L1 per. Okay. um, uh, um, and being left inverse exactly means that when I apply it to the left on CDFT of f, I get f back. All right. So what we're interested in today is we're going to start discussing is there a way of writing down what this left inverse is? All right. Now, if you look back at our initial heuristic discussion about the CDFT and all of the transforms, there's an obvious guess here. Okay. So our idea that FCD of n over t gives the content, and so this isn't a precise term, of course, but it gives the content of, of f at n over t, gives the content of f at the frequency 1 over t, well, n over t. Okay, and so we were we even had higher resolution on this statement. What we said was this means this should mean the following thing. So if f is a signal that at every integer multiple of the frequency 1 over t has that amount of stuff, then you aspire to get f back again by sort of summing over all the frequencies of the stuff that is given to you by f at those frequencies. So this should mean that we have f of t, and I'll just write that. Okay, so so it should be, so we're going to sum over all these frequencies, all right? And then there's going to be, the harmonic at that frequency, which is 2 pi I n t over t. And then, the coefficient that goes here, okay, well, that's what that is, right? But that's kind of the definition heuristically of the CDFT, is that tells you what that coefficient is. And there was a scaling factor there that showed up. Okay, but the point is that this should be FCD of f at n over t, and then the scaling factor came out front here. Okay, and so I should say that off here in a yellow aside, that some authors will define the transform to be 1 over t, interval from 0 to t, t e to the minus 2 pi I t over t, dt, sorry, that's just what we did, but that's not what I meant. Oh, sorry, that is what I meant, I apologize. 1 over t. And so the point is that we don't do that, right? So we leave this off and we put it here, but sometimes you see people put it here and then they leave it off here. Of course, in a very certain sense, it absolutely doesn't matter. But in an aesthetic sense, it kind of makes a difference which thing you go for. And as I say, if you do things the way that we're doing it, which is that you don't put the 1 over t there and you put it here, and then what it allows you to do is just use an unthinking rule, where every time you have a summation over frequency or time in the Fourier transform business, out front you have to put the sampling interval. Okay, And so here the summation is over frequencies. And so the sampling in frequency interval is 1 over t. Okay. So that's kind of an argument in favor of not doing that. Okay. So anyway, from our previous motivation of the CDFT, in other words, what this is telling us is that this is somehow the inverse, right? Because this tells us, given the CDFT of f, how we recover f back again. Okay. All right, and so we define based on this, and this is kind of a wishy-washy definition, but I'm going to write it anyway. The Fourier series of f in L1 per t is the infinite series and I'll write it like this. And I'll write it as if it means something, but it doesn't. Okay, and of course the problem is that, you know, as an infinite sum, you have to do something about the convergence of that, and as we're about to see, the convergence of this is pretty terrible in general, and so, you know, this expression, any kind of firm mathematical basis, has no meaning, and especially it doesn't mean anything to think of this thing as being a function of t. All right. But nonetheless, I want to use this notation to refer to this infinite series. Okay, and then we will talk carefully about the convergence of that series. Right. So Fourier series means this infinite series whose convergence I'm prepared to just set aside and deal with separately. Okay, so it's kind of a it's symbols. It's not actually equality of two things as a function of t. Okay. All right. And so yeah, so a few words to that effect. Okay. All right, good. So what we're going to spend the next a few lectures talking about is exactly a convergence of the Fourier series. So the first thing we're going to do is discuss, not give any proofs because this tends to get a bit involved, but discuss the fact that the series just doesn't converge. Okay, and so divergence of Fourier series. Okay, so this is a subject with a long and distinguished history. Okay, all right, so there's some real content here. So the first thing to note, well, I mean, so when you talk about convergence, of course, you have to know in what sense you're talking about convergence. Okay, are you talking about convergence in L1 per? Are you talking about pointwise convergence for a fixed t of of this infinite sum? Are you talking about uniform convergence? Okay. And so the discussion, sort of goes in those directions, right? First thing is, let's talk about convergence in L1. So if F is in, let me say it correctly. There exists F in L1 per T. So that the series of partial sums, okay, and so one of the other confusing things here that you have to contend with is this isn't just a sum like you're used to seeing in your first course on infinite series where things go from 1 to infinity. Here, the sum goes from minus infinity to infinity. Okay, so what does a partial sum mean? All right. So the partial sums I'm going to take, and these are the standard partial sums unless someone indicates otherwise, and it is interesting to take different kinds of partial sums than the ones I'm going to take. So I'm going to take what are called the symmetric partial sums. Oh, sorry, not the series of partial sums, the sequence of partial sums. Okay. And this sequence is going to be defined like so. And so now I'm going to write down something that actually makes sense. So there'll be a finite sum. Okay, all right, so for each capital N, that's a perfectly well-defined thing. It's just a linear combination of some harmonics with these as coefficients. Okay, so I'm mainly wanting to introduce that notation. Okay, so this sequence with sequence of partial sums diverges in L1. Okay, so you don't generally have convergence in L1. Okay, which is a pretty weak kind of convergence, but you don't have it. So we're going to talk more in detail about the L2 CDFT, and I've already said some things about it. So I've said that if F is in L2, sorry, the best place to do that would be here. So if F is in L2, then the CDFT is in little L2. Okay, I said that, and we're going to see that a little bit later on. Okay, and so if the CDFT is in little L2, okay, so that means that these coefficients here are in little L2, so they're square summable, right? It doesn't take much to, because these are functions with magnitude 1, it doesn't take much to see that actually if these are square summable, then this series converges in little L2. Okay, so I'll say that. And again, this is something I'm going to defer a detailed discussion of until later. Right, so if F is in little L2, and so notice that first I'll just point out this and recall for you why that's true. Okay, so first of all, big L2 is in big L1. Okay, and that's a result of the fact that the domain for periodic function periodic functions is really the bounded interval from 0 to t. And on bounded intervals, remember that we had LQ in LP for Q greater than or equal to P, right? All right, so the fact that L2 is in L1 for periodic signals, it's not true for aperiodic signals, and that's going to bug us later. Okay, but it is true for periodic signals. All right. All right. So if f is in L2, then the sequence Fn converges in L2 per t. Okay, and it converges to F. Okay, so it converges in the L2 norm. For periodic signals. Okay. All right. So there's a negative result and a positive result, and the positive result is really there just to contrast the negative result and to give a little bit of flavor for some of the other things that I'm about to talk about. Okay, because the next thing. So this. This was known fairly early in the history of Fourier series, as was this. Okay. More recent work had to do with not convergence in norm, but convergence in pointwise convergence. Okay. So in 1926, Kolmogorov showed that there exists an F in L1 per such that this series Fn of t, okay, so t is now, I'm now evaluating at some t, diverges or doesn't converge for every t in R. Of course, it's enough to check on a period, but if it's true in a period, it's true for every time. Okay. Okay, so what this means is we have pointwise convergence nowhere. Okay. So previously there had been simpler examples, for which this series diverged at a point. Okay. But Kolmogorov's example was more powerful than that. It showed that you get pointwise convergence nowhere. All right. Okay. So based on this, okay, the speculation was that you should expect, in terms of pointwise convergence here, you shouldn't expect to be able to get any good pointwise convergence results in L2. Okay, and so this was speculated about before Kolmogorov's result, and I believe it was 1905. Okay, so in 1905, it was certainly known that you have convergence in L2. Okay, And in 1905, Lujan conjectured and I should have written this one first, but it doesn't matter, that if F is in L2 per, okay, so these indices 1 or 2 make a big difference in Fourier analysis. Then the sequence of partial sums converges to f of t for almost every t. Okay, so notice you're never going to get convergence for every t, and that's just because in L2 things are equivalence classes, and so it doesn't really make sense to ask for anything to hold for every t, because you can change a given f on some set of measure 0, and it's going to define the same thing in there. Okay. So generally speaking, asking things to hold everywhere in an LP space is not something you can ask for. But you can ask for something to happen almost everywhere, and that's what Lujan did. Okay. So if in 1905 you're working in a world where Lujan's conjecture is something that you want to try and prove, Kolmogorov's proof of the pointwise, everywhere pointwise divergence of a Fourier series sort of pours cold water on that hope. All right, and so the thinking sort of became, after Kolmogorov, that Lujan's conjecture is probably false. Okay, and most of the work that was done in that direction was to do what Kolmogorov did in L1 in L2. Okay. And while doing so, okay, Swedish mathematician Leonard Carlson showed that Lujan's conjecture is true. Okay, while working to show that it's false. Okay, so accepting the prevailing view of the day, Carlson was trying to prove the falseness of Lujan's conjecture, and on the way to doing that, actually was able to show that it's true. Okay, and so 1966 in mathematical history is pretty recent. All right, and this is a hard proof. Okay, Kolmogorov's proof is digestible. Okay, but Carlson's proof requires its own book, basically, to sort of flesh out all of the stuff you need, kind of after, say, you've gone through a course like the one we're doing here, then you need a whole book to present the ideas needed to prove Carlson's results. Not necessarily a 1,000-page book, but a 150-page book. Okay. Then shortly after, Carlson Hunt showed that if F was in LP per, for P greater than 1, okay, not greater than or equal to 1, but greater than 1. Okay, then this sequence of partial sums converges to f of t for almost every t. Okay, so extending Carlson's result. Okay. All right, so given what Carlson had already done, this is kind of regarded as being less super difficult. It's just sort of more or less an observation that the techniques that Carlson used applied for all p is greater than 1. Okay, good. All right. So now let's think a little bit more about pointwise convergence. All right. So asking that something be in L2 or LP is a pretty weak assumption, which surely it must be the case that for continuous f's, okay, the Fourier series should have nice convergence properties. Okay, so and this was known to be true a long time ago. Sorry, known to be false a long time ago. So in other words, a long time ago, it was known that there are continuous f's for which the series diverges at a point. Okay. All right, but there's a stronger version of that even. So also in 1966, Kahane and Katznelson showed the following thing. Given a subset Z on the interval 0t with Lebesgue measure 0, okay, there exists a continuous f okay, so remember here, continuous means continuous on all of R, okay? So continuous on all of R and T periodic, okay? So there exists a continuous f such that at all points in Z, Fn of T the sequence of partial sums diverges. Okay. All right. So so this is as bad as it can possibly get, because we already know that if f is in C0 per, then it's certainly in L2 per. Okay, and then Carlson shows that if it's in L2 per, you have pointwise convergence almost everywhere. Okay, so you're never going to do better than except on a set of measure 0. But Kahane and Katznelson showed that you get it on any set of measures 0 that you wish. You get divergence on any set of measures 0 that you wish. Okay, so convergence, pointwise convergence almost everywhere, but pointwise divergence on a set of measures 0 that you can prescribe. All right. And so, for example, this means that there's an f in C0 per whose Fourier series, so this sequence of partial sums, converges at, diverges at every rational point, okay, and converges at almost all irrational points, okay. So that seems pretty pathological. And I guess it is. All right. And so this list of results tells you that it's a really, really bad idea to write that down. Okay. Right? And the reason is that it's literally meaningless. It doesn't make sense pointwise. It doesn't make sense in L1. Even for continuous Fs, it only makes sense generally almost everywhere, right? And so it really stresses the urgency of talking about the convergence properties of that infinite sum. Okay, and the convergence properties are, basically in general, there are no convergence properties. All right. Really the best result here, the most useful result in terms of convergence properties is this one. Okay, and that's the one we're going to talk about in detail later. That says if F is in L2, then you have convergence in L2. Right, so that's a nice result, and that's a result that you can kind of sink your teeth into a little bit, especially when combined with the fact that Illusion's conjecture is true, giving you almost everywhere pointwise convergence. Okay, right. Keeping in mind, that you can't do better than that. All right, good. Okay, so thus divergence. Okay, so now if one wants pointwise convergence, let's say, or maybe uniform convergence. We haven't talked much about uniform convergence of Fourier series yet, but we will. Okay, one must. Okay, so I should say pointwise convergence everywhere. One must put restrictions on F. Okay, because the previous divergence results tell us that just generally speaking, you're not going to be able to achieve everywhere pointwise convergence. So if you want everywhere pointwise convergence, you're going to have to work with Fs that satisfy very specific kinds of conditions. All right. Okay. All right, and we'll see for us, we're going to kind of see that those conditions are most often expressed by derivative type conditions. So, you need more than C0. You need some kind of condition about differentiability as well. Okay. All right, so there's an important bit of notation. So notation for partial sums, and the notation, if I just write the notation down, it seems kind of arbitrary. And so what I want to do is tell you where the notation comes from, and in doing so, we'll arrive at an important formula. Okay, because I don't want to write Fn anymore. Okay, so what's the formula? All right. So the formula is if F is in L1 per T, then, okay, the partial sums, all right, so let me write it out explicitly here. The symmetric partial sum from minus n to n, okay, of CDFT times these harmonics. Okay, so that's our nth partial sum. The formula that we get out of this is that this is the integral from minus t over 2 to t over 2. And you get a factor of 1 over t here. Okay. F of t minus tau v per Tn, and that's the Dirichlet kernel that we've talked about before. Okay, and so this is 1 over t of times the periodic convolution of, and I'm going to write it the other way around because I know convolution is commutative. So I'm going to write it as d per Tn convolved with f evaluated at t. All right. All right, so how might you prove a thing like that? Well, what you're going to do is you're going to plug in for CDFT the definition. Okay. And then you're going to do some manipulations with that. Okay, so it's not a totally obvious result to write, but nonetheless, it's true. And it, for example, is one of the reasons why the periodic Dirichlet kernel is important. Okay, because it is telling us precisely what the partial sums of this of the Fourier series are. The partial sums of the Fourier series are convolutions of your original function f with the Dirichlet kernel. All right, so that's another. So I told you convolution would show up in our discussion of Fourier transforms, and there. Okay, and it's kind of mysterious. A little bit, okay, and we'll try to demystify it a little bit, but it's still basically mysterious. Okay, so with this as motivation, we will denote the nth partial sum. Okay, so this. Okay, I'm going to use notation that reminds us that that's in fact a convolution, but I don't want to carry that 1 over t around because it's just a nuisance. And so I'm going to use this notation. I'm going to use d per t n f. Okay. So this is just notation, right? This is, I'm defining that, okay, as a block, right? And so I'm just writing f adjacent to the symbol I use for the periodic Dirichlet kernel, right? So what I'm defining is that group of symbols, right? I'm not writing down the convolution. The convolution is here. And for the formula to be true with convolution, it needs this factor of 1 over t. And that's what I'm kind of eliminating with this notation. Okay. Anyway, this is exactly the nth partial sum. Okay, good. All right. And so this leads you to, think about, what if I put another kernel there? All right, and I do the convolution. Does that convolution have any meaning in terms of things Fourier? Okay, and we're going to see that for the Fourier kernel, the answer is a decided yes. Okay. And what kinds of things would you put here? Well, what you're going to put there are things which are indexed by n and are approximate identities. Okay, and so we know that the Fedget kernel here is an approximate identity. And so because approximate identities have nice convergence results that we talked about when we talked about approximate identities, we expect if we put an approximate identity here, that we're going to get some kind of convergence to F. However, the Dirichlet kernel indexed by n is not an approximate identity. And so that's why we get these spectacularly crappy convergence results for the partial sums of the Fourier series. It's very much connected to the fact that that these partial sums are expressible as a convolution, and they're expressible as a convolution of something that kind of seems like it has some approximate identity-like properties, right? Remember that the Dirichlet kernel, did have this focusing behavior as n gets larger, okay? But it didn't have the nice property you want of an approximate identity, that the L1 norm of this thing is uniformly bounded in n, and that's where the problem comes up. Okay. All right. So there's lots of subtle stuff going on here. Right. Okay. Good. So the other thing I want to do, just by way of contrast, really, is so we've written our Fourier series up here, okay, using complex harmonics. You can also write it using real harmonics. Okay, and the real Fourier series looks like this. Okay, it's the same series, but you're just using different functions, cosine and sine, to express it instead of the complex exponentials, right? And the formula looks like this. So sorry. So now we're going to be getting the coefficients of the CD-CT and the CD-ST, right? The cosine and the sine transform. So it's going to be C CD of F of 0 plus some, and sorry, let me put the 1 over T out front here. Okay, and then I'm going to get the sine and cosine bits, right? So I'm going to get CCD of F at n over T cosine 2 pi n T over T plus SCD of F at n over T sine 2 pi n T over T. Right, and so, and the reason I wanted to write that down was to point out why I'm never going to write it down again. So apart from the fact that you have 2 bits of your sum in your Fourier series to deal with, this one's special. It has a extra factor of 2 here at the frequency 0. And again, aesthetics mean something, and aesthetics really suggests that when you're talking about the generalities of Fourier series, that you should use the complex harmonic functions to express your series and also to express your transform. Okay. When working with certain kinds of problems, don't get me wrong, the advantages of going with sines and cosines can show up, right? But for general discussions of things Fourier, use the complex harmonics. Okay. All right. So, so what we want to do is we want to talk now about exactly when this sequence of partial sums, okay, converges, right? So our objective now is to give some conditions on F so that the sequence of partial sums, okay, so now I'm going to use the notation that I just introduced for partial sums. Has some convergence properties. Okay, so e.g. pointwise convergence, uniform convergence, convergence in LP, and there may be other things where you want to talk about, and we'll even talk about some of them, or just one of them. Okay, so that's one of the things we're going to do. So another objective, and I want to talk about this now just because now is a good time for this to come up. Because what am I saying here? What I'm saying is that this sequence of partial sums for general F and L1 has pretty crappy convergence properties. I get no kind of useful convergence, okay? And so this way of approaching the problem says I need to consider less general Fs, right? So I need to put conditions on F to get some kind of convergence of this sequence of partial sums, right? So another approach, and again, it's one we'll talk about, is to find a better candidate for the left inverse. Okay, because these divergence results seem to be telling us that we made the wrong choice. Okay, in the sense that this inverse just isn't an inverse. Okay, and so maybe you should try to find a better one. Okay, and what we'll see is that there is a choice, and it's not that unnatural. And in fact, the choice just comes from putting Fourier kernel there instead of Dirichlet kernel. Okay, and that shouldn't shock us given our discussion of approximate identities and the fact that the Dirichlet kernel did give us an approximate identity. Okay, but there's also reasons why you want to work exactly with this sequence of partial sums and not this one. Okay, so there's all kinds of things playing out here that we want to try to probe into a little bit, right? So given all of that discussion, what we'll do next time is we're going to start talking about pointwise convergence of that sequence of partial sums. All right, so that's where we'll start talking next time.